ではお時間なっておりますので、次のセッションのスピーカーはシャイ・アルモグさんで、タイトルは The Duck Talks Back Do You Really Know How to Debug Effectively というセッションを始めていきます。それではビデオをお願いいたします。
Hello everyone, I'm Shail Mog, and 25 years ago I got lucky. I was sure I was a great programmer, then I had a debugging session with a senior developer, and I was completely floored by the way he wielded the debugger. He used features and techniques that I was totally unaware of. I had no idea. We don't learn debugging in university because they can't teach that knowledge. A tool we spend so much time inside on our day-to-day job is essentially left as a take-home exercise. I was lucky to get a glimpse of competence that made me study this tool and the surrounding process. Hopefully I can pass some of that luck on to you. But first, let me say a couple of things about me. I wrote a few books, including one about debugging, which covers all of the topics we'll discuss here. I worked in this industry for decades in many companies, and as a consultant, I founded a couple of companies, wrote a lot of open source code. You can contact me over my socials listed here and follow me on Mastodon, Twitter, LinkedIn, etc. I also have a YouTube channel you can check out with a lot of lectures and material about Java and debugging. This is my A+ book titled Practical Debugging at Scale, which I mentioned before. This entire talk covers some of the first chapter. There's a lot to discuss about debugging, especially when it comes to production. This talk is divided into 4 acts, but I'll skip the last one due to lack of time. In the first one, which already started, I'll discuss a personal pet peeve of mine about debugging. Because hopefully you all know the basics of what debugging is. I assume everyone here knows how to set a breakpoint, step over it, look at a watch expression. This talk goes deeper than that. But first I want to start with a 3-minute rant. It's short and then we'll get to the technical stuff, I promise. Why do people hate debugging? There's an antagonism towards debugging and debuggers. In some cases, that makes sense. I used to debug on embedded and mobile devices, and back in the day, that was a terrible experience. But still, most of us treat debugging like taking out the trash. We hold our nose and run, trying not to smell it. We don't develop debugging skills because we don't want to debug. We want our code to work. We treat this crucial part of our job as punishment. I think the reason is that we feel stupid when we find that the bug is stupid. In most cases, it's something dumb. The debugger shows us and we feel like idiots. No one likes to feel like an idiot. And the debugger is there pointing at the bug, and I guess most people think of it like that. Personally, I don't think of it like that. I don't think of it as Nelson. There's a universal gesture of debugging. When I show it in my talk, everyone agrees. This means debugging. I think of debugging as Zen, as a way to humble myself. People tell us how smart we are all the time for doing this type of work. It's very grounding, a very grounding experience to know that I'm really an idiot. So I'm thankful for debugging sessions. They keep me grounded. The debugger is the most wonderful tool in the world. Imagine a mechanic going into the engine and literally inspecting the motion of the cylinders. They can't do that. We can do the equivalent in the debugger. We need to use the debugger to celebrate how well our project works, not just the bugs. In fact, one of the chapters in the book talks about using the debugger as a learning tool. When I open a new code base and need to understand what's going on, just reading a huge project isn't practical, but spending a few hours in the debugger can teach me everything I need to know. Let's go into concrete debugging examples, specifically about control flow. We'll cover a lot of features very quickly. Some you might know and some you might not. I won't go into basics though. I assume everyone knows the basics of using IntelliJ IDEA and a debugger. Force return lets us return immediately from a method and potentially return a different result from the method. So when we're experiencing a problem, we can return fake data from a specific method to simulate a problematic condition. Unlike step out, we return from this point. While skipping the rest of the method, we type in the return value and the rest of the code won't execute. This lets us change the control flow of the app. We can return different results or skip problematic code to see what happens next. Imagine a case of a hard to reproduce bug. This means we can simulate the conditions that can trigger that bug. But this gets better. We can actually move the current instruction pointer to a different position in the method. In IntelliJ, we need to install the Jump to Line plugin for this to work. This is an amazing feature and remarkably underutilized. I know people don't know about this feature because the install numbers for this plugin are sadly very low. Once the plugin is installed, we can drag the arrow on the left to bring execution to a new location. If you saw a bug, just drag the execution back and reproduce it. We can skip over code that's failing, etc. Imagine building a unit test. Just drag the execution point back and forth and tune the variables you passed into the method. That way you can get a sense of the right arguments you need to pass to get good coverage. It's the ultimate do-over button. You don't need to stop, recompile, or anything like that. A watch point is a breakpoint we can place on a field. This is pretty standard, but a surprising number of people aren't aware of that capability. We can place a watch point on a field, which will stop every time the value of the field changes. This is a remarkably cool way to catch a case where some code mutates a variable. We can tune this so it stops not just for changes to the field, but also for reading the value of the field. Trace points are probably the most important feature of a debugger that developers don't know about. Trace points are often called log points. They're a special type of breakpoint that doesn't break. They don't stop the execution and just log to the console. You can add a trace point by shift-click on the gutter. Notice I can write any valid expression here, either a string, variable, or method invocation. This is effectively a log I can add in runtime without restarting my app. It has full access to the variables and everything. It's printline debugging without the risk of accidentally committing the debugging code to Git. It's fantastic. Notice you can also set a trace point by unchecking the suspend checkbox you see here. A breakpoint breaks by default, which means all threads are suspended. A trace point lets you disable that behavior. Notice you can also create a breakpoint that only suspends a single thread and not all of them. But that's a different subject. Logging is debugging, and trace points are exactly that. If you have race conditions which are normally very hard to debug with regular breakpoints, a trace point is a perfect tool to track those. Method breakpoints are similar to what we think of as line breakpoints, but they have some important distinctions. Method breakpoints are normally emulated by the IDE. It just uses line breakpoints to simulate method breakpoints. But there's a huge use case for real method breakpoints. Say we want to break on all the methods starting with the letters I and S in classes whose name starts with prime. This might seem far-fetched, but is actually a useful use case. If you have an abstract base class whose subclasses follow a naming convention and they have many related methods, you want to track everything. You can do that using this approach. Notice you can also use trace points here and get very deep logging. such as log or stack trace every time a specific set of APIs is invoked. Breaking on all exceptions or on some problematic exceptions is terrible. The IDE stops every second. I'll enable breaking on any exception to show this. People don't do that, and the reason is we hit it a lot. It becomes useless for a real life application like this. We can solve this with the catch class filter. We can just exclude all the exceptions caught by the Java APIs, and this filters out these exceptions that are handled in the JDK. Exceptions in the application will still stop here. It's amazing that this isn't the IDE default. Without it, the feature is useless. Next, we'll discuss debugging of asynchronous code. One of the reasons I love Java is that it's so darn easy to debug. We just step into a method and we can move between threads. That's easy. But some of that is habit. In recent years, the approach of using async await and similar asynchronous techniques gained traction, even in the Java realm. Debuggers kept up with this and let us see glued together stack traces. Let's dig deeper. Here we have a standard async example from JetBrains that uses a list of tasks and just sends them to the executor to perform on a separate thread. Each task sleeps and prints a random number. Nothing to write home about as far as demos go. This is pretty trivial. Here's where things get interesting. As you can see, there's a line that separates the async stack from the current stack on top. The IDE detected the invocation of a separate thread and kept the stack trace on the side. Then, when it needed the information, it took the stack trace from before and glued it to the bottom. The lower part of the stack trace is from the main thread, and the top portion is on the execution thread. Notice that this works seamlessly with swing executors, string async annotation, etc. This is very cool. How does this work under the hood, and what do you do if you have custom code that's asynchronous? The IDE works by saving stack trace in place where we know an asynchronous operation is happening, and then placing it later on when we need it. How does it connect the right traces? It uses variable values. In this demo, I created a simple listener interface. You'll notice it has no asynchronous elements in the stack trace. By adding the async schedule and async executor annotations, I can determine the point where an async code might launch, which is the schedule marker. I can place it on a variable to indicate the variable I want to use to look up the right stack trace. I do the same thing with execute and get a custom async stack traces. I can put the annotations on a method and the current object will be used instead. Seeing the values and the current state is one of the most important tasks of the debugger. In this section, we try to get deeper insight into the debugger features. The data we see as we debug is how we reach the conclusions. A lot of times it's an absolute mess. I assume you all know how to add an expression to the watch. I even assume that you know that you can add a watch expression directly to the editor body. I don't cover that here. It's cool, but not as groundbreaking as renderers. One of the most annoying things to me is when I return from a method and have no idea what was the return value. This can happen because the developer didn't define a variable and just used the return value as an argument to an internal API, which I can't step into or even use it as a part of an equation. This feature solves that problem, and amazingly it's off by default, because this is a very common problem. Luckily, the IDE has an option called show method return value, and it saves that value for us so we can inspect it right away. Once I check it, you can see the return value of is prime appearing in the watch area. Let's zoom in a bit. Right here in the fully qualified name of the method we return from, the value returned from is the value we returned from that method. If there's one killer feature you will get from this talk, it's this: object marking. It's also one of the hardest concepts to grasp in my talk. Object marking lets us declare a new static variable in runtime and store the value of an expression into it without restarting or recompiling the code. To explain object marking, let's add a watch of the current thread method. We right-click this watch entry and create a marker object. Object marking lets us give a global name to a specific object, so we can later use that name even when the object isn't in scope. That means I can later check if the current thread is equal to the myThread variable and get a proper result. Notice that the IDE adds a debug label suffix to the name. Still, this is the exact same variable. This is immediately useful when dealing with many objects. In this case, I can literally check if the method will be hit with the same thread. I can use it to compare any object instead of writing their pointers on a piece of paper. I often use this with APIs like JPA, where we might sometimes have two objects, object instances with the same identity. This is really hard to detect. Just mark one object and then you can instantly see it's a different instance. I used to love game cheats as a kid, and this specific feature makes me feel like it's a cheat mode in debugging. We can show all the objects of a given type by right-clicking a thread and selecting Show Thread Objects. We can see all the thread objects in the virtual machine. We can even go do that on a string array and show all string arrays in the VM. Notice that in both cases we see internal objects from the VM. We even saw the JIT compiler thread. This is a remarkably useful feature, especially when tracking memory issues. This is something that was standing right in front of my eyes, and I didn't see it for ages. Filtering is a very powerful feature when we have code that views arrays or collection content. We can just filter the content using an expression and reduce the noise significantly. In this case, I have 4 elements in the pet clinic demo. I narrow them down by testing against the pet ID. Notice I use this to represent the current element in the list. This is very versatile. If we have a list of names, we can filter it so we can only see applicable names. Streams in Java 8 are constructs inspired by functional programming that lets us chain process a stream of elements. They're pretty cool, but one of the problems in them is that they are notoriously hard to debug. IntelliJ ships with a stream debugger that you can find in this button that I'm pointing at with the mouse. When you press it, you need to be positioned on a stream in the debugger. As you can see, I am in the line above. Pressing this button launches the stream debugger. On the top, you can see the stages of the stream expression. Notice that as I traverse through the stages of the expression, the objects change and draw a line between their original mapping to the new one. Initially, the list was of visits, and now we see the conversion to pets in each visit. Since the final stage is a set, we will only get one instance of each pet. That isn't shown here. The advantage here is that you can see the entire process in a single view that you can take back and forth. Unlike a loop, which you normally debug by stepping in the debugger, this view here is a bit more complete. Rendering is one of the features that we just don't expect. We think of watch expressions as a fixed thing, but when we're debugging a huge system, things can become tedious. A debugger can only show what it knows about, and for the most part, it's just guessing. With renderers, we can determine how an element is displayed in the watch, but we can go much further with renderers. To get started, we can customize the renderer through the right-click menu here. For the most basic customization, we can toggle and enable multiple features within this dialog. Then press apply to instantly see them in the variable view below. I can see the declared type of the field. We can include fully qualified names for class files. We can see the static field values. We can include hex values for primitives by default, and so much more. Renders slow down the program execution. So if you feel that step over is slow, just mute them like this. Then you can see individual values for renderers by clicking the specific item. Let's take this up a notch. We have a repository instance, and the visit repository variable below doesn't provide valuable information. We add a renderer that applies to JPA repository, which is the base interface of this instance. Then we just write the expression to represent the rendering here. We'll show the number of elements in the repository using the count method. Notice I don't provide an object instance. The IDE automatically runs it in the context of the object. You can also use this to represent the rendered object. You can run this on demand, which makes sense for expensive expressions. Look at the visit repository variable preview and see the value instantly adapts to these changes. Now, you might think I can use toString to do that. That shouldn't be a problem. But no, you can't. That means that toString will create an SQL query every time you invoke it. So every time you write something to the log, it will create an SQL query, and that's expensive. It can be expensive in production because if you log that object intentionally or by mistake, you can actually damage your production system. But in a debugger, this code doesn't matter because it's running in the debugger and isn't running in production. So we can do very expensive things and things that might break just so we can get additional information while debugging without impacting the actual code. The view repository is rendered with the right string containing the element count, but it isn't properly expandable. We can execute the findAll method on expansion, and the response will appear below the object like any other array or list. To make this even cooler, I can define an expression that indicates if the data is expandable using the count method. Let's talk a bit more about custom rendering. You'll notice that everything looks exactly the same, the numbering, the list of entities, etc. But when we open the list of renderers, it's blank. There are no renderers. How does this suddenly work without a renderer? How did I cheat on this? What's going on? We use code annotations to represent the renderer. This way you can commit the renderer to the project repository. You don't need to configure individual IDE instances. This is pretty simple. We add a dependency on the JetBrains annotation library into the POM. This isn't a problem because these are only annotations and they have no runtime overhead whatsoever. We add an import to the renderer and we scroll down and we added a simple renderer annotation code. Notice that this is pretty much the code I typed in the dialog, but this time it's used in an annotation. So my entire team can benefit from the improved view of repository objects. If you're building a library or if you're working in a large team and want to expose data in a way that's easier to debug, you can use this annotation library to perform these sorts of things, improve the async work, as we mentioned before, and get a better developer experience result for your entire team. When we think about memory debugging, we usually think about profilers, which do have some functionality for that. But the standard debugger has some amazing capabilities. Memory debugging is a very expensive tool, so it's off by default. When you don't need it, disable it so your debugging performance won't suffer. We start by launching the memory view from the IDE UI menu. Notice that the memory view is empty by default, even after we launch it. This keeps the IDE responsive. In order to see the actual objects in RAM, we need to click the load link in the center. Once loaded, we can see the instance count for every object. This helps us get a sense of what exactly is taking up RAM. But that's only part of the story. When we step over, there are allocations happening in the methods we invoked and possibly in other threads. We can see the difference between the current point and the one before when we look at the diff column. We can double click an individual entry and see all the instances of the given object, which is a remarkably powerful feature. But this is tedious. I have a fast machine with a lot of RAM. I can just enable update loaded classes on debugger stop. And I will no longer need to press load explicitly. Only do that if your machine is a monster. Track new instance lets us explicitly track the individual allocations that are going on between 2 points. We can enable that by right-clicking any non-array object and enabling this option. Once enabled, we can see a small watch sign next to the tracked object, but there's a lot more involved. As we continue the execution, I can now see only the objects allocated specifically in this diff and can understand exactly what happened in terms of RAM. I can also click an individual object and see the stack trace that triggered it all the way up to the literal call to new for every object in the stack of this type. That's spectacular. Problem. Threading issues are notoriously hard to debug. This reputation isn't necessarily justified. Once you understand the basics, you'll find that most threading issues are pretty similar. Let's start with the basics of thread debugging. In the stack frame, we can look at all the current threads in the combo box above the stack frame. We can toggle the currently selected thread and see the stack for that thread and the thread status. Notice that here we chose to suspend all threads on this breakpoint. If the threads were running, we wouldn't be able to see their stack as it's constantly changing. We can enable threads view in the right-hand side pull-down menu to see more. As you can see, viewing the stack is far more convenient in this state when working with many threads. Furthermore, we can customize this view even more by going into the customized thread view and enabling additional options. The thread group option is probably the most obvious change as it arranges all the threads based on their group and provides pretty deep view of the hierarchy. Since most frameworks arrange their threads based on categories in convenient groups, This is often very useful when debugging many threads. Other than that, we can show additional information such as the file name, line number, class name, and argument types. I personally like showing everything, but this does create a somewhat noisy view that might not be as helpful. Now that we switched on the grouping, we can see the hierarchy of the threads. This mode is a bit of a double-edged sword since you might miss out on an important thread in this case, but if you have a lot of threads in a specific group, it might be the only way you can possibly work. I'm assuming that with Project Loom increasing the number of threads significantly, this mode would become more and more popular. The first step of debugging a race condition is a method breakpoint. I know what I said about them, but in this case I need it. Notice the return statement in this method includes a lot of code. If I place a breakpoint on the last line, it will happen before the code executed, and my coverage won't include that part. I only use it for the exit portion because if I use it for both, I'd have no way to distinguish between the exit and enter events. I make this a trace point by unchecking the suspend option and then log the name of the thread. I now do the exact same thing for a line breakpoint on the first line in the method. A line breakpoint is fine since entry to the method makes sense here. I change the label and make it also into a trace point instead of a breakpoint. Now we look at the console. I copy the name of the thread from the first printout in the console and add a condition to reduce the noise. If there's a race condition, there must be at least one other thread, right? So let's remove one thread to be sure. Going down the list, it's obvious that multiple threads enter the code. That means there's a risk of a race condition. Now it means I need to read the log and see if there's an enter for one thread happening before the exit of another thread. This is a bit of work, but it's doable. The next step is debugging deadlocks. Here we have two threads. Each is waiting on a monitor held by the other thread. This is a trivial deadlock, but debugging is trivial even for more complex cases. Notice the bottom two threads have a monitor status. This means they're waiting on a lock and can't continue until it's released. Typically, you will see this in Java as a thread is waiting on a synchronized block. You can expand these threads and see what's going on and which monitor is held by each thread. If you're able to reproduce a deadlock or a race condition in the debugger, they are both simple to fix. I hear people say, oh, I debug with print or logs. To me, that sounds like the person is publicly declaring that they don't know what's a trace point. Marker objects, renders, and many of the features we discussed here are amazing. Please use them. Memory debugging, field watch points, etc. can change your debugging like nothing else. Exception breakpoints can be useful with the right filters. Have them enabled all the time. So many times I ran an application and found out that something was printed to the console and I didn't notice it because I just reran the application and the console got lost. When you have that enabled all the time, you can't miss that. So if there's an exception, you'll find it right away. This is a huge benefit. Use renders and similar tools to see the variables you're working with. It will boost your productivity. Thanks for bearing with me. I hope you enjoyed this presentation. Please feel free to ask any questions. Also, feel free to write to me. Please follow me on socials to keep up with my upcoming books. I barely touch the deep subjects I cover in my books and in my YouTube channel. I hope to see you all there. Thank you all.
Thank you.
Thank you. So, yeah, Shai, thank you for your presentation. So now it's time for Q&A. So I'll ask audience if they have any question or comments. So ご質問とかコメントある方いらっしゃいますか？日本語でも大丈夫そうかな。Yeah. So, as you know, maybe they have something, but you know, they're shy. So,
Yeah, well, I know about Nisha.
So, as you mentioned about your YouTube and Twitter as well.
Yeah.
Yeah. So, I will tell them to reach you via socials. なので皆さん SNS とかでもしコメントとか質問とかあったら寄せてください。And yeah. So yeah. Anyway, it was a great presentation. As I noticed, I haven't debugged effectively. Yeah, there are many ways.
None of us have. Yeah. That's the point. I think all of us don't really invest the time in it. We only treat it when it's time, when something fails, and then cast it aside and forget about it. And then wait for the next time there's a disaster. And I think this is starting to change thanks to observability. Because this talk was mostly about the side of debugging that we run into in the debugger. And in my book and in my other talks, I talk about the continuation of debugging, because debugging in production in the cloud on servers goes much further than just, features in the IDE. This is just the first chapter. So the interesting part about that is that observability is actually something that people do care about, but sadly enough, it's mostly DevOps, not developers, at least not enough. And I'm hoping to change that, because as developers, which I am, and I hope most of you are, it's actually really useful to get access to production data. It makes us better developers, it makes the product better, and it helps us connect with the customers, with what they're actually experiencing, which makes our connection to the actual product and code much stronger. So I think of this as a holistic process. Fixing problems in the debugger locally is one thing, working with command line tools and other things like that, understanding the theory of debugging, which is a huge subject in its own right, and then all the way to the problems in production. It's sort of a single process.
Thank you. So in your book, there are many much more ways and tools.
Yeah, there's 14 chapters, and this was the first only. The second, yeah, the first actually.
Okay. Thank you. So let me translate a bit. なのでまずいいか。セッションも英語だったしね。はい、皆さん本にもっと方法があるって、方法とかツールの紹介があるみたいなので、オブザーバビリティを高める一つのきっかけとしてこのセッションが皆さんに何か気づきがあったらいいなみたいなことをおっしゃってましたね。なので本脱英語の本だと思いますけど、よかったら見てみてください。So we don't have the Japanese edition, right?
Yeah, I need to come next time with subtitles. I'll arrange for that somehow.
Thank you. So we still have 5 minutes. So do you want to add more contents or say something?
Yeah, so if there's no question, then the last time I gave this talk, I got a couple of really good questions about that. I won't have time to do, I thought about doing the fourth act, which is about remote debugging, but I won't have time for that. You can check that out in my YouTube. But a very interesting example I was given by a developer was a case where he experienced an issue when debugging parsed data. And he saw all this very obfuscated data and constantly needed to understand what's going on there. And this is a very common thing when we're looking at sort of a hierarchy of parse data, DOM, or any proprietary type of parsing. It's really, really hard to understand what's going on there. So he asked for suggestions there, and obviously renderers are a huge value for this particular case. If we can add them into our view and start seeing things as we debug, it changes everything. It makes our understanding almost instant. But it gets a bit more complicated when it's an issue like that in production, because normally what we do is just add logs. And that makes sense. You know, we'll print out the log, we'll print the data before we parse it, then see the problem. Unfortunately, that creates a problem of, first of all, overlogging, of logging too much data. But worse, it creates a personal information issue, where a PII issue, where you might accidentally log information that you're legally disallowed from logging. And that's why it's very dangerous to use tools like that when you're trying to debug a problem of that sort. Because if you're logging just unparsed data, and then you might accidentally log usernames, passwords, email accounts, credit card numbers, things like that. And lots of times you just can't. So one of the things that I gave him as a tip was to look at a different talk I have about logging best practices, where I talk about how to log in a more effective way, and that way debug in production more effectively. And also look at my talks about developer observability, which is sort of a debugger set of tools that exist in the observability world that let you debug similarly to the way you would debug with the debugger, but in production, while maintaining the safety and the privacy of your customers. So
yeah, what you were saying totally makes sense. Yeah, it's getting more complex after being launched on production in terms of the personal information and complexity. Yeah, so yeah, I really agree with your idea, and that will be helpful for all of us. Yeah, they are agreeing. Yeah, they agree. Do you see that? Yeah. So anyway, yeah, it's time to finish. So thank you again, Shai, and I hope you visit Japan in the future.
I hope so too. My daughter hopes so even more than I do. She's crazy about Japan.
Sounds great. So we all are waiting for you. So thank you so much.
Thank you.